All right, so carrying on with this idea of centripetal acceleration. If we wanted to come at this from not just like a formula way of thinking, more like a vector way of thinking, we definitely could do that. So we got, the beginnings of a drawing of something going around in a circle. We'll give ourselves a north, south, east, west reference frame. And I'm not going to add positives and negatives onto this thing. That's the danger of circles, is that, what direction you're traveling changes continuously, like literally continuously. So it's hard to decide on a north, south, east, west, positive, negative. Let's just talk for now about what's happening first. First, we've got a V1, and we'll say that this V1 is going off at 5.00 meters per second. And then we'll call that moment 1. At moment 2, we'll call this V2. If this object's moving around at a uniform speed around the circle, V2 is going to be equal to 5.00 meters per second. Now, if I want to talk acceleration, and I'm just doing like a linear calculation, that would mean that the acceleration would be delta V 5 minus 5, 0. That doesn't seem to make sense, because clearly we think that centripetal acceleration is a thing, and so there must be something else that's happening here. Something else that we could think about is how long this is going to happen. So let's just say that the period of time it takes for this to occur would be 12.0 seconds. And maybe something else that's a feature of a circle, the radius. So we can say that the radius of this thing, r, is equal to 9.55 meters. Nice round number. And another thing that we could try to tackle on this would be the circumference. So we could say, okay, well, circumference is equal to 2 pi r. So 2 pi, and somebody with a calculator help me out. 2 pi times 9.55 meters. Maybe to like 3 decimal places. Yep.
60.004.
Nice. Okay, so 60.004 meters. That's our circumference. And let's talk about like how long it would take to get from point 1 to point 2. Well, if the period is 12 seconds, then let's say that the delta t for going from point 1 to point 2, which looks like it's a quarter of the way around the circle, would be the period divided by 4. So 12 divided by 4 is 3. Nice round value. So we've kind of tackled a lot of stuff here. Like there's a bunch of basics that we've broken down. One thing that I want to throw out there that maybe we might not have thought of, and maybe it's not apparent why, but if I look at V1, I want to point out that this arrow that I've just drawn in here would be negative V1. See what I mean by that? It's like the same vector magnitude, but it's the opposite direction. So it's V1 and negative V1. And why we would do that has to relate to the definition of what acceleration is. So acceleration, as we've learned before, is delta V over delta T, which is the same thing as saying V2 minus V1 over delta T. And as I look at this, I'm used to adding vectors tip to tail. I'm not used to subtracting vectors tip to tail. That's a weird idea. So I want to propose that instead of saying V2 minus V1, we reframe our understanding of delta V as being delta V equals not V2 minus V1, but V2 plus negative V1, where negative V1 is the same magnitude as V1, but in the opposite direction. I just drew that in red, right? So then if I was going to do V2 plus negative V1, tip to tail, V2 would look like this, as stolen from that picture on the left-hand side there, plus negative V1, which is the same thing as minus V1, because subtracting is just adding in a negative kind of way, right? So minus V1. Magnitude-wise, this guy is 5 meters per second. Magnitude-wise, this guy is 5 meters per second. And then, if I were to draw in the resultant vector, I'll do it as like this big, bold, double vector. That would be our delta V. Now, I don't even need to do any math yet to realize that if one side of this triangle is 5, the other side of this triangle is 5, and this right here is a right angle, doesn't this got to be 45 degrees? That makes sense. And one of the things that we often drop from this acceleration calculation is the fact that when we calculate acceleration like this, we're actually calculating the average acceleration. And something that we also don't talk about, because we talk about things linearly, is that the average acceleration happens at the average location, really. So what we've done is talked about the average acceleration between points 1 and point 2 to generate delta v, and we're still on our way there, but notice that delta v would be at 45 degrees relative to the cardinal directions, but the average location, the midpoint along that arc, is right there. And so the directionality of that delta v from the average location, boink, goes straight towards the center. Centripetal acceleration gets its direction from the delta v, just like linear acceleration gets its direction from the delta v. And based on our knowledge of centripetal acceleration, and even the name itself, it points towards the center, right? So here we are. This is, some solid ground to stand on. Now, if we were going to do the calculation on this one, we'd do the Pythagorean theorem, and we'd say delta v is equal to the square root of the magnitude of v2 squared plus the magnitude of, I'm putting magnitudes because it's negative v1 just so that we don't get messed up on the negative signs, although really we could just put in the 5s. And then if we were to do this math, and I won't trouble us with having to write out the whole thing, you'd end up getting 7.071. 0711 even, meters per second. And if I go back to this kind of linear model for calculating acceleration with our kind of two-dimensional thinking now, we say, all right, well, acceleration then would be equal to delta v over delta t. I'm going to be bad and put two equal signs on the same line. 7.0711 meters per second divided by, remember the delta t for a quarter turn we calculated earlier is 3 seconds. So somebody help me out. 7.0711 divided by 3. Yep.
2.357.
Nice. 2.357 meters per second squared. I'll put a box around that. I want to come back to it in just a second, because what we had on the previous page was this seems very involved. We had a freebie equation. Remember I gave you this free equation that I said, oh, this is too complicated to derive on our own just now. And I said, okay, AC is equal to v squared over r. What I want to do is just plug in the instantaneous velocity, 5 meters per second, into this equation, 5.00 meters per second, per second, squared, divided by the radius, which was our 9.55 meters. And can somebody help me out with this one? Don't worry if it's not the same as the previous one. What's the answer we get using this formula? Yep.
2.617. And then just a question, for the one on the bottom left, is it radian over quarter? Is it always radian over quarter turn?
Well, for this one, I just chose a quarter turn kind of arbitrarily. I mean, we could have done an 1/8 of a turn or a 1/16 of a turn. Pardon?
How would you know, that question?
Well, it might give you a picture, or there might be a very clearly worded description or something like that. I just kind of chose it so that we could play around with the numbers. So yeah, it was a quarter turn just because I said so, I guess, is the answer to that. Sure, units. Now I compare these two, and people are frustrated. Oh man, Mr. Killen's did it this way, and got one answer, and we did it the gifted answer way, the way that we got sort of handed, and it got a different answer. Which one's more correct? Well, the answer that's more correct is the second one. This is a better answer. I'll put a star beside this one. This one's a weaker answer, but it could be better if we were willing to work harder. It's kind of an issue of limits, and I know that depending on whether you've reached ahead on your math or not, you've talked about functions and limits and things like that. But a limit is what happens when you go to the extreme. And so right now, we've taken these two vectors a quarter turn apart. It turns out that we can get our answer to be closer to what's the accepted truth if we take them an 1/8 of a turn apart and we subtract v2 plus negative v1. and we do it that way, it'll get closer to the truth. And then if we do it a 16th of a turn apart, it'll get even closer. And if we do it, like 1/1000th of a rotation apart, it'll get so close that it'll be like practically this value. The problem is that it's really easy for me to take two vectors and do them perpendicular to each other and create this triangle. But whatever direction the vector would be pointing when they're 1/1000th of a rotation apart, it's harder for me to do the math on it. So I'm not going to do that as a demo. Again, this is going to be a bit of a trust exercise. Do you trust me that in the limit, where those two vectors are super close to each other, where the arc length is approaching 0, this method's going to get us to this method? And that really is one of the ideas in calculus, where in limits, we approach the truth, right? And so I'm not going to approach that limit because it's just, frankly, too hard, and I'm like inherently lazy. This is my sales pitch, that yes, these formulas or these approaches are connected, and that this equation is connected to the limit, where the distance between those V1 and V2 values are an infinitesimally small distance apart. Everybody cool with that? So more of a sales pitch than anything, and just to say that what we're doing isn't radically new, it's just a different way of doing stuff. Yep. All right, so let's move on down the page, recognizing that this v squared over r equation is going to be our bread and butter for circular motion. We say, okay, if it took 120 seconds to complete 10 orbits of an object around the center, and I don't even know, we don't have a story for this, so it could be, like when I was a kid, I used to take a skipping rope and attach a tennis ball or something to it and like whiz it around my head and see if I could knock my sister in the head or something like that with it. I wouldn't do that. My sister's a lovely girl, and whatever I did on the playground has nothing to do with, never mind. All right, so we say that this thing goes around 10 times. So I'm just going to, this isn't formal notation, I'll say delta t sub 10, 120 seconds. And that's just going to be my way of communicating that it happened 10 times. N equals 10. That's how many times it went around in a circle. So I say, okay, well, I've got my period. That's going to be delta t sub 10 over n, 120 seconds over 10, 12 seconds. By the way, as I'm looking at this, and you might just make a mental note, 4 sig figs. Remember, the n does not contribute to sig figs. It's an integer count. Okay? 4 sig figs is present in these givens. We can say, okay, well, if I want to calculate the frequency, it would be 1 over period. So 1 divided by 12 point, really if it's 4 sig figs, 12.00 seconds. Somebody help me out, what's the frequency for this? One divided by 12. Gosh darn it, I can't do that in my head. Yeah.
0.083 repeated.
Nice. And it's the 3 that's repeated, right? All right. And hertz. And just a reminder that when we're, and we could write this as 0.0, it's 4 sig figs, 8.333 hertz. Or we could write it as 8.333 times 10 to the power of negative 2 hertz. And then we also want to remember that the unit of hertz is just Heinrich Hertz's last name, and it really means 1 over seconds. But 1 over seconds is an awkward thing to say, and we don't like to write cycles per second because then people think that a cycle is a unit. It's not. So it really is, a hertz really is a 1 over seconds, which is awkward. So we just say hertz, named after Heinrich. And before we leave this page, I'm going to put a bubble around this to say that although the thinking up above isn't bad thinking, I want to say that this way for centripetal acceleration, where c stands for centripetal, a sub c, centripetal acceleration, this delta v over delta t is a weak method. Really, it's only weak if we're not willing to let the distance between the velocity, v1 and v2, approach 0. And it's just too much work. So it's a weak method. Okay? It's not that it's a wrong method, it's weak. So what we're going to do instead is we're going to use the following equations. I'm just going to write this as a summary list. V squared over r 4 pi squared r over period squared, and 4 pi squared rf squared, all of which appear on your equation sheet. But really, the second of which are easily derived from the idea of v equals, well, maybe I'll put that in writing. V is equal to 2 pi r over period. And subbing that into this master equation and recognizing that we get this third one from recognizing that 1 over f is equal to a period. Okay? So not tricky derivations, really. Oopsie. So I'm not going to say that this is like conceptually hard. It's just different than something we've done before, and not even that different. All right, so we've got driving a car around in a roundabout in London, and I happen to have gone to London this past summer, rented a car because I drove basically the perimeter of England and up to Scotland and back again. Skipped over Wales. Sorry for the Welsh people, but. My first 2 days was driving in London, and oh my gosh, if you can imagine driving in Toronto, but on the wrong side of the street for your first 2 days of driving in this place, it was a quick learning curve. And I only got stuck on one roundabout where I went round and round and round and round until I could finally figure out how to get off of the stupid thing. There were like a million roundabouts on this holiday, but it only happened to me one time. And Miss Killens will attest that I only almost killed this twice. But it was great. Fantastic. Anyway, here we are in this roundabout going around in circles. We've got a radius of curvature, 12 meters. That seems like a fairly reasonable radius for a driving circle. Period, take 18 seconds to drive around this circle. And we're asked to find the centripetal acceleration of the car. Okay, so AC is equal to 4 pi squared r over period squared equals 4 pi squared, and we'll just sub in our values, times 12.0 meters divided by 18.0 seconds. Don't forget to square it. And somebody help me out. I'm not doing this one in my head. What's the centripetal acceleration for this car? Anybody got it? Yep.
1.4622.
Nice. 1.4622 meters per second squared. Now we got to deal with the direction, because since this thing is like tangentially going around all the time in different directions, we can't say, remember I said north, south, east, west is problematic? With circles, it makes sense to think about a reference frame as just being towards center and away from center. Especially when we're just thinking about cars going around circles like this, we might end up being in a situation where there's pulleys involved, where we have to think about left-right tendencies or something like that. I mean, that could be in our future. But like for now, for this car, we could just say it's towards the center. Oh, and I guess in terms of sig figs, we've only got 3, so it really should have been 1.46 approximately meters per second squared towards center. Now, sometimes people say, well, wait a minute, towards center, why is it towards center? I've been in cars that have taken turns, and I feel pressed up against the glass on the outside of the curve. You guys ever had that experience where you're like getting pressed up against one side? And I would argue, and we'll talk more about that in the dynamics unit, but that's because of what we call the centrifuge effect. So there's centripetal force, there's centripetal acceleration drawing you towards the center. Or you could think of it as centripetal force as being something that knocks you off course towards the center. And if I think about this object going around a circle, what direction would the force have to be pushing in to knock it off course? Like it's going this way first, then later it's going this way. Wouldn't there have to be something like knocking it towards the center of the circle? Like effectively, I could like line people up around the outside of this driving path with baseball bats, and they could smash my car towards the center of the circle, right? There's no way that they would smash me from the inside of the circle outwards. There's no outward force that's going to keep me in a circle. It would have to be something smashing me towards the center of the circle. Would that visual work? Like, That's the only way this works. And so it helps me to realize, wait a minute, if the force would have to be directed towards the center of the circle to keep me on path, and F equals ma, we know that from before, and A and F have to have the same direction because F equals ma, mass is a scalar, stands to reason that the centripetal acceleration is also towards the center. So whatever I've been experiencing when I get mashed up against the outside wall of a car when I take a corner, that's not centripetal acceleration or centripetal force. It must be something else. And again, we'll talk about it more in the dynamics unit, but what it really is an effect of inertia. At any given point, look, I tangentially want to fly off in this direction. I tangentially want to fly off in this direction. But what gets in the way? The wall of my car. And so because of inertia, I want to fly off in a tangent, but the wall gets in the way. And so effectively, I get mashed up against the wall of the car. And if you've ever been on, like I went to Wonderland for the Labor Day weekend with my kids, got the Fast Pass. They went on every ride. It made me sick just watching them. And you could see that, like, that my son is like, he's the size of a man. He's in grade 7, and he's taller than his mom, and he's probably going to be as tall as me. But he's a big boy, right? And he's athletic, rides his bike every day. But then his little sister, she's in grade 5. She did not want to be on the outside of the curves. She wanted him to be, yeah, I got that the right way around. She wanted to be on the inside of the curve, want him to be on the outside of the curve, because even at grade 5, you don't want to be mashed by the big person, right? This is something we've experienced. And if you've ever been to an amusement park ride or a carnival ride or whatever, you know that stuff, right? And it's good to know, like when you're on there, it's not the centripetal force, it's the inertia that's crushing you up against the wall. Okay? Anyway, yes, sir.
I was just wondering if there's an acceptable shorthand for towards center.
Let's work on that. All right, so the car's average speed. Back to that, we say v is equal to 2 pi r. And this is really like, some people call these the plug and play kind of equations. We're not rearranging anything. There's no fancy algebra here. We're just subbing in 2 pi, 12 meters. Says it was 18 seconds. Don't tell the math teacher that I have 3 equal signs on the same line. You know who I'm talking about. I love her, but she would definitely be angry. All right. I'll show her this later, and she'll be upset just looking at it. Just say, oh, Trevor, what have you done? 4.18879 meters per second. All right, 3 sig figs, 4.19 meters per second. And then people say, well, what direction? Oh, what a pickle. I'm not even going to write the direction because it changes continuously. Now, if I wanted to know what direction it was going when it was at position, I don't know, let's call it this guy position 3, then I could say, oh, north, right? But in the absence of that, I'm just going to leave the direction blank, okay? All right, so a kitty was attached to a Newton spring scale. Oh, isn't that cute? And a driver was driving around in circles with a radius of 12 meters. Okay, so maybe in London. And the kitty experienced 12 newtons of force as it was driven around. Okay, so you can try this. You can put a cat on a seat and attach a force meter. See how that works out for you. And just drive in circles with a cat attached to a force meter. Probably you'd attach it to the collar, not to its ankle or something. But anyway, that just seemed dark. I didn't want to attach a cat to a force meter because it seems like I'm hanging a cat or something. But anyway, it's attached to its paw. We're not damaging the cat, all right? Anyway, centripetal force has the same formula as linear force, except that the acceleration that would be linear ends up being the centripetal acceleration. And if I'm writing out my givens for this little kitty, I'd say, all right, well, I know that the kitty experienced 17.0 newtons of force, because that's what it read on the spring scale, and the radius of curvature of my road is the same as the one above, is 12.0 meters, and we've got a mass for our cat. The mass of the cat is 4.50 kilograms, and I'd like to figure out what the centripetal acceleration acting on my cat is. Well, if I take this new but not so new equation for centripetal force, I'd say AC is equal to FC over M, and I'm really only specifying AC and FC because sometimes we'll have different forces. Like think about somebody who's in like a circular trapeze act. That could be something that shows up. Maybe not in this unit, maybe like later on. Aren't they going to travel in a circle? They'll have FC acting on them, they'll have FG acting on them, they'll have tension force acting on them, all while on a trapeze. And it'll be very gripping and exciting, right? We're not going to do that right now. We're just swinging cats in circles. But I'm just going to call it FC for now because like I want to set up good notation for later, right? Anyway, we sub in our values, 17.0 newtons divided by 4.50 kilograms. And I won't labor this too long. I get 3.7 repeated meters per second squared, which will round off to 3 sig figs of 3.78 meters per second squared. And we could say toward center. And of course, we could make a therefore statement for ourselves. I'll just leave the ellipses because I don't feel like writing it. I also want to take a look at the units here. Reminder, if I've got newtons divided by kilograms, the unit analysis, the dimensional analysis, newtons is kilogram meters per second squared divided by kilograms. And so, yeah, we definitely do end up getting units of meters per second squared. So, I mean, I'm not going to keep on doing this dimensional analysis stuff. I just want to like make sure that we get that even though it's circles, the units are still all good and we're all still happy, okay? It says, find the period of motion for the car carrying the kitty. Well, I want to lay out those equations that we had before. I'll call them equation 1, v is equal to 2 pi r. I know I didn't call it equation 1 before, but I'm going to call it equation 1 now. Divided by period. Equation 2, we'll call it AC is equal to v squared over r. Equation 3 is AC equals 4 pi squared r over period squared. And equation 4 is AC equals 4 pi squared RF squared. And if I want to find the period of motion for this car going around in the circle, is there an equation that's the best equation that I could cherry pick out from this list? Which one do you like? Equation 1, 2, 3, or 4? Based on what we know so far. Fickle finger of fate. Which should I choose? 1, 2, 3, 4. Avery wants to say. Avery's passing. Yeah, Alex? 3. 3 is the best choice. If we want to do the least work. Let's take a look. Quick inventory. I know the centripetal acceleration, pi is a given, 4 is a given. We know r, we want to know period. We just got to do a little bit of rearranging, not a whole lot. And we, if you like, we can even just cross multiply it. And we can say period squared is equal to 4 pi squared r over AC. Square root both sides, period's equal to the square root of all that. I mean, if I was in a math classroom, I would probably have just rewritten this as 2 pi times the square root of r over AC. You see what I'm saying? See how the 4 pi squared would reduce to 2 pi? But as it stands, I'm just going to sub things in the way that I've done it. So I say 4 pi squared times the radius, 12 meters, divided by the AC we calculated earlier, unrounded, remember, 3.7 repeated meters per second squared. Square root that whole thing. And somebody give me an unrounded value, maybe like 4 decimal places. Yep. 1950. Nice. Seconds, and we'll round it off to 1950s. It looks like the 1950s. Round it off to, what did we say it was? 3 sig figs? So 11.2 seconds approximately, and again, we could say a therefore statement. Da, da, da. And what does Miss Frizzle say? If you keep asking questions, you'll keep getting answers. Good wisdom. I think that's that. Let's just double check. Oh yeah, there are a couple of Fermi questions. So here's what I'm going to suggest you do. Grab a partner, and between the two of you, choose one of these two questions and answer it to the best of your ability, okay? If you don't remember how Fermi questions work, there's basically no numerical information given. You have to guess, estimate what the reasonable numbers are, okay? And I give people a few minutes right now, and we'll figure out as a class what the reasonable answers are to these questions. Go!